Let us start today's lecture with the problem where we had left in the last class. The last problem that I was discussing was, let me explain the question again and we will gradually come up with the solution. The problem was somewhat like this, that there is a half cylinder. So this was the half cylinder having the radius of capital R, and I gave you this impression that this half cylinder is having this length in the third dimension, which is L. L was quite large in comparison to radius that was given. Question was very clear that if the total charge on the half curved surface area of the cylinder is capital Q, and the charge on this dielectric sheet, this sheet here, this is plus Q. So his question was, can you find out the electrostatic force of interaction between the plate and the half cylinder? So half sheet is rectangular with a width of 2R and a length parameter, which is L. And there is a half curved surface area. We need to find out the force of interaction. So I'm not drawing the third dimension. We understand the problem. So how to approach the question? So I said, while you are solving this problem, think about finding out the force on this guy. That is the sheet. Now I'm saying that if you cut any differential element here on the sheet, to find out the force, you need to find out the field because of this half cylinder. And because of this hollow half cylinder, field at any point on the sheet is perpendicularly downwards. Let's try to understand why I'm saying that the field at any location on this sheet is normally downwards. I'm not saying I know the magnitude. If this is a differential area DAI, to be honest, in 3D, it is somewhat like this. It is somewhat like this. And you can cut your DAI anywhere. Like if this is DA1, E1, you go anywhere on the sheet to cut your differential area DAI, and you say the field is normally downwards. This is the point that I wanted to explain. Why I'm taking this as down. Because if I can justify that the field everywhere is normally downwards, then the calculation of force becomes pretty simple. Because even if you cut a differential area, the force dFi vector on that area will be normally downwards as per the diagram. That will be sigma of this sheet. Let me call it as some sigma. So sigma, which is uniform on the sheet, into DAI, into EI, and then I will take the net summation of all such terms. Now, why I said field is downward is because inside a infinite hollow cylinder, right, where the charge is spread on the circumference, we know that the field at all the points inside is 0. So there are two ways to look into it. I will prove by contradiction. If this cylinder at these points or in this plane would be having any field which is not normal, let's say the field is like this, because like all these guys will repel. So there are only two options. The field is normally downwards, or field is in this quadrant, like these octants, to be honest. But I'm saying if field was having any such direction here, then by principle of superposition, when you overlap the lower guy, at the same point, it will have a symmetric field. So if these guys are having a field like this, then the lower guys will have a field which is like this. And then the resultant field will be definitely rightwards. But I know that the resultant field at this point is 0. So that is only possible if the field, because of all these guys at this point, is kind of vertical. If it is vertical like this, then from the lower half, it will be vertical like this. And then only the net field can be 0. For any other combination of direction, by symmetry, the net cannot come out to be 0. But I know inside an infinite hollow cylinder, the net field is 0. Why I'm saying infinite? Because he has assumed that the length is quite large. So I don't know the magnitude of field now at these locations. I don't want to use integration. I don't know EIs, but I know the directions. And if I know the direction everywhere on the sheet, then the force will be this expression. Now the problem becomes simple because net force is downwards. I'll take sigma outside, sigma for this sheet. So for the lower sheet, the total charge that you have given is Q. So that sigma can be written as Q divided by 2R into L. So sigma is Q by 2RL. Now I've got sigma over I, EI/dAI. This much can be my answer if somehow I can find out the value of this term. Now again, it is interesting. What does that term represent? The second term that I have written, what does that term represent? So basically, this term talks about the flux. Basically, talks about the flux. What flux? I am saying, and remember, while I am calculating field here, this field is not because of the sheet. It is because of the cylinder only, because I am finding out force on the sheet. So this is the flux because of the half cylinder across that base area. So the question now is, given a cylinder, half cylinder, having some spread of charge, capital Q, and having a long length, like capital L, which is large, how can we find out the flux because of this guy across the sheet, the central cross-sectional area? Now again, it is interesting. Now to find out flux across this, I will say cut a differential line element on the circumference, on the curved surface area of the cylinder. So in 2D, I'm showing you a point, but you understand in 3D, it's a line element. And first of all, I'll say find out the flux because of this guy across the sheet. Now carefully observe it. If you look into the 3D physics of the problem, very interesting. Like this is infinite line, and I want to find out the flux through the sheet, which is there. So if you connect the end elements here and here, in 2D, it seems that you form a triangle at an angle of 90. In 3D, you understand that this is not a point, it's a line. This is a plane. This is also a plane. And this is also a plane. So I just want to find out that what flux is going to enter this guy, this much. What flux is going to come here. So whatever is going to come out in this 90-degree angle, the same is going to spread across this guy. And now directly I'm saying by the symmetry of the problem that if this was a linear element, infinite linear element, all field lines will be in a plane which is perpendicular to the line. And in that plane, there is a theta symmetry. So total angle in that plane is 360 degree. And out of 360, I'm catering to 90 degree. So my contribution of flux will be 1/4 of total which can come out from this charge. So if this charge can yield me some flux, and total flux is charge upon epsilon naught. So I will get 1/4 contribution in this 90-degree part, and that will pass through this plane. Again, remember, it seems like I'm talking in 2D, but basically I'm talking about the problem in 3D. And luckily 3D problem also has a planar symmetry. Like all these planes do not intervene with their fields. Fields will lie in the plane, in the plane, in the plane. So total cylindrically symmetric flux, which will come out from that line, will be spread in an angle of 360 degrees. And I'm interested in the angle of 90 degrees. So my net flux will get multiplied by a factor of 1/4. And the same thing holds for other guy also. If I take another guy, again, if I draw this angle, I know the angle in a semicircle is 90. So again, out of the total flux with cylindrical symmetry, this 90-degree will accomplish 1/4, 1/4, 1/4. So basically, I can directly say that the flux here is 1/4 epsilon naught of the total charge that is there on this semi-cylinder. And what is the total charge I am having on the half cylinder? That is capital Q. So now the answer to the question becomes very simple without integral. It is Q by 2 capital R capital L into capital Q by 4 epsilon naught. So you understand your result is QQ upon 8 R L epsilon naught. Very clearly, you can see this option comes out to be correct. The most interesting part of the problem was the last segment. And in fact, IIT can ask this question directly for flux also. It's not very straightforward. It is conceptual that if there is a long cylinder, it's a half cylinder, you have charge on the surface. What is the flux because of cylinder across the cross-sectional area of that half cylinder? So by point symmetry or cylindrical symmetry, you can easily get your answer and then you will get the result, right? Okay. Let me take flux. Okay. Let me explain. What I am saying is this is my half cylinder and I am taking a 2D diagram. Practically, you understand that in 3D, these are like linear elements. If I say there is a point charge, actually in 3D, this is a line charge because I have a cylinder, a hollow cylinder, half cylinder. So think, because of every line charge which is present here, you have to find out flux because through this area, it is 2R here, but in 3D, this is also L and this dimension here is also L. Now just think conceptually that if I have a line charge, long line charge, the total flux which will come out of this line is total charge upon epsilon naught. And because you are presuming that it is very long, the field lines will only be in this plane. That is the YZ plane. I mean, in this problem, if it is Z, it will be the XZ plane. So XZ plane, XZ plane, XZ plane, field lines are present. Now I am saying the total flux which is coming out is Q by epsilon naught, but whatever is crossing is only 1/4 now. Like if I show you, whatever is crossing across, if this problem would have been in 2D, first look into the 2D view and just extend it over length. In 2D, this angle in a semicircle is 90. So out of total thing which comes out, my spread, this will all be wasted because whatever has to enter here has to come inside this. And this is 90 out of 360. So 1/4 of the total, and total is charge upon epsilon naught. That will go here. For the next guy also, again it will form 90. So 1/4 of total, 1/4 of total. Then a person will say, how I am using this symmetry in 2D? Because this is cylindrically symmetric, even the infinite line charge will have a total flux, which is charge upon epsilon naught, which will spread cylindrically outwards. So if you study one cross section, every cross section is identical in nature. So I've studied one cross section of like a point because I know that the field lines, because of a point on an infinite line, cannot go backward or forward. They will be in which plane? YZ plane only in this case. If I'm taking Y and Z and X outwards. So simple. So I use the 2D symmetry, the total angle distribution, and 1/4 there. So for the next guy also 1/4, 1/4. So the total line will contribute 1/4 from here. And that happens for every line. So I directly said that 1/4 by epsilon naught and the total charge on the hemisphere. So I used that cylindrical symmetry, this condition, and the problem became very easy. You'll get your answer. Okay, let us move on to the simple next. Let me take some very basic questions first today before I take up more typical problems. Now just observe this question. Question is based on a very standard symmetry. It's a pantograph. I mean, these are like, I'll explain what is happening here. There are 2 long and 4 half. Where are those rods? Like one rod is like this. This is a long rod. This is also a long rod, right? And there is a pin joint here. So there is a common hole and a pin here, right? Other than that, they have axles here, like they have common axles here. The same is valid here. At this point also, symmetrically, this point they have connected here, and symmetrically they have connected here and at this point. So these are the 2 long rods, this rod and this rod, and 4 small rods, these 2 and the lower 2. Then between this point here and this point here, they have connected a thread. They've connected a thread. And then they've connected another thread here and connected a small mass, small m. This system is suspended from a ceiling. It's a very normal setup, like a pantograph setup, which we will find in most of our houses. Like keychains are like of same shape, keychain and these common structures. So what he wants is, if the pantograph is suspended from the ceiling, the lowest hinge on the pantograph is connected to the hinge above it, the lowest hinge and the hinge above it. You can say this is also the hinge. And there is a load which is connected by a string, mass m. The question is simple. Given everything, you need to find out tension in this thread. The question is, if there is a ideal thread, ideal string here, can we find out tension in this thread? So tension needs to be calculated. I understand, all of us understand, if the system is in equilibrium, the tension in the lower thread is mg. No issues with that. But what about the tension here? That was the problem. Now, he has already said that this system is forming two identical rhombus, right? So you understand that these lengths like are equal. Symmetrically, you understand these lengths are equal. Now, because rotation is possible about these hinges, we can write force and torque balance equation after taking appropriate hinge reactions to solve the problem. But the matter of fact is, those calculations will make it quite lengthy, typical, difficult, to be honest. So there is an indirect method of solving such problems. And if you look into the concept of work, I'll give you a minute. I mean, just think, how will you solve this problem? Obviously, when I'm taking up this problem, I want to discuss a concept that given such combinations, we should not always think in terms of force and torque balance. And that is fine. I mean, these are fundamental concepts for any system which is in equilibrium. No problems with that. But at times, you should think in terms of other concepts also to solve the problem. And how do I look into this problem is, indirectly, I think in terms of work. I mean, this system may be a balanced system, but I will hypothetically displace this system. Now, what I'm trying to say is, I'll say, assume that this point has got some distance from the top. When it is in equilibrium, it will be at some distance. So let us call this distance as y, this diagonal length. And because this is identical rhombus, the distance of the second point from here will be 2y. Now, by some mechanism, if I displace this point differentially, then that displacement can be written as d of this distance. So basically dy. And symmetrically, this point, I mean, this point or the lower point is one and the same. And that will get displaced by a distance of 2 dy. So to find out tension in the equilibrium state, I'll explain theoretically also what I have done. In the equilibrium state, I have displaced this equilibrium setup by a small amount dy and 2 dy, because their distances were given, and I have written the work. Basically, I'm trying to write a du kind of term, and I'm using the property of stable and unstable equilibrium, where when you are in equilibrium, your du should be 0. So how I'm trying to write that du? I'm saying there's a pull force downwards here. So that gives me a plus t dy. And if I look into the second end, I get minus t 2 dy. And there is a weight also. So I got plus mg into 2 dy. And then I said that term seems to be 0. If this happens, dy will cancel out, and 2t minus t, so t will come here, and this will simply come out as 2 mg. It's a one-line solution. Mark my words, this is not straightforward. I mean, if you don't use, what I have done here is, I have thought in terms of du of the system. So if you hypothetically think you're trying to write the du of the system, with respect to the equilibrium state, and you are trying to write down the works which are being carried out. So this gravitational term has decayed its energy by mg into 2 dy by differential displacement, right? And whatever has been acquired by that string, so that I have tried to write t dy and minus 2 t dy. And then I said that du term plus du term or minus du term in this state should be equal to 0. I have not even bothered about writing other forces at other points because those forces are equal and opposite from both the guys. And whatever displacement happens, they cannot carry out any work. So there was no need for that. At this point, as such, you don't need to write any term because that point is not even displacing. Other than that, all the rods were ideal, so their weights were not involved in the problem. Only thing was this thread, which was critically placed in such a way that the two ends here were having a different differential displacement. Although practically this is not happening. Remember, it is not actually happening. This is in a state of equilibrium, but hypothetically I have displaced it to a newer position to write my expression. So then it becomes very simple and you get your result. So just I've taken this problem for you to think that such kind of things can happen. One more similar case, and then I will come to more complicated situations. Now, problems which are of this sort, like if you read this problem, there are basic methods like method 1. Just go through like very fundamental problem. Somebody says a ball is projected vertically upwards with a velocity of 20. The ball returns back on the ground with a velocity of 16. There is an air resistance acting on the ball that is proportional to the speed of the ball. Now, this is interesting. Air resistance acting which is proportional to the speed. So more of a viscous drag kind of problem. So the problem can be put up this way, like there is a liquid filled up in a container and you are inside the liquid and you throw a ball vertically upwards within the liquid and it never comes out of the liquid. So there is weight, buoyancy and drag 6 pi eta RV. So ball goes up, it doesn't cross the surface, it stops somewhere and then comes down. And the point from where we have thrown, the final velocity at that point is seen to be 16. Now, air time is like time taken by the ball to reach the position again. That is what is the question. Now, we have solved such kind of problems. We calculate the steady state velocities and whatnot. So, what I'm trying to, so obviously when I solve this, I will solve this problem within liquid and I'll know this thing that the weight is greater than the buoyant force. Then only this situation is possible. In this case, he is not talking about buoyancy. So he is talking about the net weight. So apparent weight of your problem and weight of my problem is symmetric. So if you observe such questions, you can do it by basic kinematics, fine. Somebody can solve it by some energy calculations and something. That's also fine. Now I want to observe it by another method. I mean, if I was solving this problem in the exam, I would have solved it by a very fundamental idea in a line. I will say, in this process, when the ball is going up or ball is coming down at any t is equal to t, just let me write the forces properly on the body. So there is a weight vector, mg vector, right? Then there is a resistance which is minus kv vector, right? And irrespective of direction of motion, these forces are like same, equations are same. That is mass into acceleration vector, which is dv by dt. This problem is very simple to what I have done in flux. Like this idea we can use anywhere. You understand now. Just multiply this equation and you are done with it. Because basically you are going to get mg delta t. You are just averaging it over delta t. You are multiplying by dt and integrating indirectly. So, and this term basically comes out as 0. This was the problem some term, na? If you find out the time ki upar kitna time liya at the highest point, then you will calculate height. Then from that height you will leave the particle, it will come down. Now the force will change, new acceleration, again time. But you understand we don't need it. because this term minus kV dt, V is a variable, but if you take integral of this term, V dt is the total displacement, which is 0. So this variable force is actually irrelevant in the problem. And now it is nicely written. M, I multiplied by, so M dV, and then you take delta V, delta V. So it was great. MM cancels. Your question was delta T. So it was minus 10 J cap delta T. And final velocity is downward. So minus 16 J cap. And initial velocity was 20 J cap. So basically minus 36 J cap. And minus J cap cancels. So delta T is 3.6 seconds. The reason why I took this question is not the solution that I have written. I wanted you to have such ideas in problem while solving question. And remember, these ideas are not only applicable up to mechanics. Whenever you are solving circuits, always think in terms of these ideas, because there you may have L di by dt term, right? Yeah, L is some constant into dq by dt term. And then there is a q by c kind of term. And then there is some constant force or a constant term involved in the circuit or constant voltage involved. So when he is solving, you understand this is how you should look into the problem. Fine. Now let me take a different problem which is based on thermal physics. Nicely written problem. Let's understand what he is trying to say in this problem. Here there is an ideal gas which is trapped in a vertical cylinder under a piston. So I'll just scribble a few things. This is, let's say, my ideal gas. There is some piston. There is some mass also. I'll put it there. So this is piston having a mass of capital M. The inner surface is lubricated with oil, so no friction. Cylinder is made up of a material of finite thermal conductivity. Okay, so you understand that the rate of flow of heat from the gas to the surroundings will be gradual, finite thermal conductivity. Initially, the piston stays in equilibrium at a height h above the base, and the system is in thermal equilibrium with the surroundings. So T naught surroundings, T naught is same, and it is at some height h from the base. Perfectly fine. Some mass it must be having, right? What else? So if I just write the initial situation, I would have said that this pressure here is P outside. If P atmospheric is P naught, I know it is P naught plus mg upon area. This seems to me to be the absolute initial state. So I'll use it afterwards. Now what he does? Now he says when a small weight is gently placed on the piston, it quickly settles to a new position, which is delta H1 distance below the initial. So you put a weight there, it will come down to a new position, right? And that position is acquired nearly immediately. So use this data that if this distance is delta H1, and now I've got a mass also kept over it, and that is immediate. Just think. So this was your first step. I don't know what is delta H1. You have to think. In fact, the positioning of M was done here itself, so that as you keep this block, it acquires a new position, which is delta H1 below the initial position. And now he says, I don't do anything, but because of the finite. So now this seems to be more of some no heat interaction step. And this seems more of a heat interaction step to me, where because of finite thermal conductivity, it will interact through heat with the surroundings. And what it does, it further moves down after a long time by delta H2. So what happens is, if this distance was delta H1, and now in the final state, it is below this position again, somewhere here, with some mass obviously kept, and that distance is delta H2. This is our final state in the problem. This was the absolute initial state, right? Piston and everything is given to you. The question is, if delta H2 was equal to 0.1 delta H1, we need to find out that what is the molar specific heat at constant volume of the gas. And we need to predict the atomicity of the gas. That we will take care of. So can we find out the CV of the gas? That was the question, given these relations. So if you observe the question carefully by conservation of energy in the two steps, in the first step, I can say, just let me write the terms. Delta Q is equal to delta U plus delta W in step 1. And here I know that if this is an immediate kind of process, there is no interaction as such that has happened. If number of moles of gas were N, so this seems that there is a term which is NCV. This was T naught. This state, it has some temperature. Let's call it as T prime. Final state, again, it will be T naught. So this is T prime minus T naught. This term is 0. And then I have to write this term. And I'm directly saying that while this was happening, initial and the final pressures were kind of the same. So I am saying it is because as you position it, you will have a constant, the initial and the final pressure there could be observed to be the same. There is no heat interaction that has happened. So we are ready to write this term because that pressure which is going to come as such, because the mass that you have kept, if you read the question carefully, he has said it is a small weight which is being kept. So that seems that I'm just going to write that P delta V term, basically P delta V on it. So it seems like some minus P delta V I'm going to write here. We'll write it appropriately on the basis of delta H1. I'll use it. Because that then seems to me that I'm just writing this as A, area of cross section, into delta H1. I'll talk about this pressure P. So I'll elaborate, but this is quite straightforward. And when you observe the second situation, here if you again write delta Q is equal to delta U plus delta W, right? Here now what I observe is, because it is gradually coming down, the pressure consistently is constant. So I think it is NCP delta T for the gas. This is NCV delta T. I'm talking about the second step. We are talking about step 2. I'm writing question from here to here in step 2. This was step 1, not the state 1. So step 1. And plus delta W. So this term here can be written as P delta V term. Because in this case, while I'm analyzing, I know the pressure is constant. So I could have directly written P delta V here. Now you observe, there's not much of an issue because this will simply come NR delta T. And this term is coming out as P delta V. Your equation is very similar to P delta V is equal to NR delta. And everything taken care of, it seems like there is some P term, delta V in magnitude, because I have written P delta V. So I should take a negative sign. So I'll use it here, minus A delta H2. And this comes out as NR delta T. So just focus on delta H and delta T, rest will be taken care of. So I'm writing minus PA upon NR is upon delta H2 and delta T of this step, which is some T naught minus T intermediate, which is T prime. And if I write this term here it is NCV T prime minus T naught is minus PA delta H1 type of term. So if I write again, it is minus PA upon N is CV into T prime minus T naught upon delta H1. Now try to just eliminate these two terms symmetrically. So take a R here, and just try to eliminate this. So you should get T naught minus T prime upon delta H2 is CV T prime minus T naught upon R delta H1. And now you understand in both the cases, the term that you have written is similar. I mean, these two are like negative terms of each other. So delta H2, delta H1, I mean, I have taken the magnitudes throughout. I'll use that afterwards. Basically, what we are trying to do is, as they have given you, you just take mod of all these equations. I don't need like mod throughout. Just take the magnitude of these equations so that we are not looking into the sign terms as such. We are just bothered about the changes. So just take the mod term as such. And now put down the value. What they have given as a relation between delta H2, delta H1. They say that delta H2 is 0.4 delta H1. So substitute that. This term is 0.4 delta H1. Right? Now everything falls in place. This delta H1 term, CV seems to be coming out as R factor upon 0.4. This is 10R by 4, and that comes out as 5R by 2. Basically, the question, I'll explain also. The idea of the question simply was, what is the molar heat capacity at constant volume? It should be 5R by 2. And then he also said, what is the atomicity of the gas? So technically speaking, it should be a diatomic gas. I'm not talking about the vibrational degrees of freedom. And if it is a polyatomic linear also, that works. So it is a diatomic, I can say this much, or if it is other thing, it is like a polyatomic linear. So I cannot talk about the atomicity if it is a linear molecule and polyatomic. That is fine. What is the idea behind the problem that we have used is, remember one thing, that pressure term, this is actually, this process, I'm not saying pressure throughout is constant. So that's why I'm not writing delta Q as NCP delta T. Here I know that this is, in other sense, you can say this is a reversible process. This is irreversible. I've just applied the energy conservation. And in this case, I knew that at all the possible positions, at all the steps, it was isobaric. So I could have taken NCP term. And throughout, I took the magnitude. So just look into the sign. There was no heat interaction. Delta U was coming as such. Delta W was happening. And because surrounding was trying to press it, so I just wrote minus pressure of the gas into delta V term. Practically, I knew one thing for sure, that T here is a state function, right? So I will not need it, because the delta T term is going to come in the work done part in both the situations. And second equation is, if you observe carefully, in second situation, indirectly, I could have directly said that P delta V is equal to NR delta T. Even if I don't apply this equation, doesn't matter. You gradually understand that whatever I've written is NR delta T is equal to P delta V. Basically, my interest was that delta T term here and delta T term here will have the same magnitude. So whatever temperature has risen from here to here, the same is the decay of temperature. So ultimately, what I wanted to do in the problem was to equate the temperature differences of the first and the second step to get a simple solution. And you get your answer there. So that is how we can approach this type of basic problem while solving the question. Okay. Let me take one problem where the shape of the rope as such is not given. It is, look into this comprehension, you will understand what I'm trying to tell. There is a block which is kept on a surface. Let us read. This is kept on a surface which is rough, right? And then there is a string which is having unique shape and a mass. So it's like a uniform inextensible rope. Mass is given 2 kg and length of the rope is given, shape is not given. Length is 4 meters. I'll come to it, how to use this length. Now it is attached to this block which is kept on the table. And this block is having a mass of 7.5. We'll use all these things. Coefficient of friction here is 0.5. The upper end is held at a distance of 2 meters above the block, and assume the dimensions of the block to be 0. There are a few more things which are given. The upper the upper end of this is, and the lower end is such that the tangent at the lower end remains horizontal. So tangent is horizontally, right? Now in this situation, the block stands still on the floor. Acceleration due to gravity is 10. Now the question starts. The question is, what is the angle at which the upper end must be pulled? The upper end must be pulled at an angle that is closest to. Now, basically, what is the target of this guy? The target is to move this block. And he wants me to find out the angle at which I should try to pull. Just read this carefully and think, how will we approach it? We have force equations with us, which we are going to apply. But you understand that as I don't know the shape of this rope, right? Even by balancing in the X and the Y direction, I may not be getting the solution to the problem. So what should we do analytically? How should we solve? And because there is one option also, insufficient information. And that is most complicated, because it seems that generally when I will think while solving the problem, this may create a problem. I mean, this situation may create a problem. I may think that the information may not be sufficient, but actually it is sufficient. So let's think what is happening here. Now, just why I was taking this problem is, in such kind of problems, you should just think about a differential segment of the string. Just think about that. If you cut a differential segment anywhere on the string, you know that as you move up, the tension is changing. So if this segment is making an angle of theta, and the tension here is T, or you can say the tension here changes to T plus dt, whatever it is, I know that the vertical segment, like there is T cos T sine, the vertical tension is changing only because of the weight. So the change in the vertical component of tension, which here was T cos and T sine at this point, if I take this angle as theta, so differential change in T sine theta is basically because of the differential weight. So if I take that differential length to be dl or ds or whatever, I can write the mass per unit length into that length on the curve, dl multiplied by g. So that is my first equation. I also know by horizontal balancing, there is no other horizontal force. So the horizontal component of tension, T cos, remember, T and theta are variables. They are variables, they will change. But T cos theta will remain as a constant, the horizontal component of force. So I may use some constant C. This is a constant force. Throughout on this rope, this will remain constant. So I have two equations now. Now I will use them carefully to get my result, because depending upon these two, we can find out the result. Like using these two equations as T cos theta is constant, or you can say d of T cos theta is 0, one and the same. By these two equations, what I'll get is d. Let me just come out of T first, if I'm dealing with theta. So this is C tan theta, d of C tan theta. Theta is the general angle of the tangent on the rope at a general position. So this was C upon cos of C tan. That is lambda dl g. And now I can make it more simple, because that C will come out. So C d tan theta. So C secant square theta d theta will give me lambda dl g. That is right. Now you know that theta here at the bottommost point is 0. And let's say this angle theta is alpha. And while this guy is just about to move, this T cos theta, which I'm saying is constant, is actually the horizontal force, which is just equal to the limiting friction here. So C for me is equal to, because tension is only horizontal, the normal reaction will be mg. So basically mu mg. And what is this coming out as? If you just observe the data, I don't know where they have mu, yeah. So 0.5. The mass of this block where is that? Attached to a block 7.5 kg, and G is given as 10. So this comes out as 5 into 7.5. So it comes out as 30 newtons. No, what is that? It is coming out as 5 into 7.5. So it comes out as 37.5. Yeah, just let me write it carefully. This constant value comes out, so you can understand that this is known to me. I'll substitute. Let's come to the problem. We understand that we can find out C. Now, it was secant square theta d theta. This term is known. In fact, even if I don't do this, I could have directly eliminated terms here. It does. Even beautifully, we could have written, because if you just summarize these terms, integrate this term, you will get C tan theta. So this is one way looking. I could have said C tan theta, the value difference from I point to F point. I'll move from this point to this point. That will give me lambda G into summation of all the DLs is the total length L. So tell me, in the first question, everything is known now. So I'll just substitute all the data for all of you to get the answer. You know the value of C. You are interested in tan theta final, that is tan alpha. Tan theta initial, that is 0, is equal to RHS is lambda into G into total length. So lambda into total length into G. And mass of the rope as such was given to you. If you look into this, the mass of the rope was given to you 2 kg. So this is the total mass. So this becomes 2G. This becomes 2G. And LHS as such becomes C tan alpha. So keep tan alpha as such. And C was this value 5 into 7.5. So you understand, if you need the value of alpha, tan alpha is coming out now. It is coming out as 2G upon 5 into 7.5. And that will yield me the value of alpha. So calculate this first, then we will move forward. Alpha comes out as such. So it is coming out as how much? 24.4 upon 7.5. So this is 40 upon 75. Then what? 5, like 8 and 5, 15. I mean, just look into my calculations. Just check that. What I wanted to tell you here is the data is sufficient to find out the angle at that point. If you want all this information separately, like if you want me to find out the friction at the bottommost point, I think it can be seen easily. C was being calculated as 37.5. So this is known to you. This value is again coming out. And thirdly, the 47th part of the question, if you look into my calculation, well, here what is happening? The upper end is slowly shifted downwards. Slowly shifted downwards. So basically, he's trying to change this vertical height. I'll come to it. And what else is being done? While shifting that end downward, simultaneously away from the block, maintaining the tangent at the lower end horizontal. I mean, everything has been maintained. Only thing is the height has been changed. So here the question is, when the block begins sliding, at what height above the lower end is the upper end? So what we are doing here in the second situation is, again, let me tell you what we are doing. Practically, while analyzing this problem, the concept is straightforward. This point, if you analyze, while I analyzed it at a general position, how will you solve the last part? Again, I will see the same. I will say change in the vertical component, T sine theta. Just check. I've taken theta, T sine theta. Again, I'll say this is lambda DLG. I'll substitute properly, DLG. And secondly, I again know that T cos theta here is again a constant. That value is C. Now use this equation in a different way. What I'll do, I'll take care of this DL now. Because I know that theta here is known, so I know that DL sine theta can be written as a dy term. So I'll write this equation as D T sine theta. So T I'll write as C tan theta. And then I will write it as lambda G. I want to find out the value of DL. So that DL sine theta is dy. So this is dy upon sine theta. And now we will try to convert everything in terms of y coordinate, theta and y coordinate. So I think you understand that C will come out. Again, it is secant square theta d theta, and that becomes lambda G dy separate, and take a sine theta down. So now you know that the height, if you just take sigma on both the sides, lambda G into the height, the rope, whatever rope has been given, if I just take the height of that rope h, so lambda G h, which may be required in the problem, height. This is actually this term. And now just observe what are these terms equal to. C constant is known to you. It is sigma or integral of what? It is sine theta, secant square theta, d theta. So secant theta, then tan theta, d theta from initial to final. And you understand it is straightforward. C, secant is secant tan. So secant theta final minus secant theta initial, that will give me lambda GH for the rope. And C is the horizontal component. So maybe the limiting friction in the problem. So observe, if in the last part I ask you to find out capital H, rest everything, mass of the rope, length of the rope, so this given, initial theta 0 degree given, limiting friction force given, and theta final has been maintained the same. So we already calculated theta final because he has given that. At what height above this will happen? So it is slowly shifted downwards, right? H has been changed and theta can be calculated at which it starts moving. Remember one more thing. In the previous part, when I calculated theta where it will start moving, you understand that was not dependent upon the shape of the rope. You know this thing that in the previous equation also, while you have solved the same thing, my result was C, it was a D tan theta, it was delta tan theta I'll have is lambda DLG. So it was very evident that lambda into total length into G upon constant is basically tan theta final minus tan theta initial. Here also, it seems like a state function kind of approach. Path was not relevant. Give me the total mass of the rope and the total length. These all will become constants if C is constant. And this was known. So this is also known. So you understand in the third part of the problem, I'm using this information. Whatever I've calculated in first part, I've used the tan theta finally. Substitution, you guys can do better than me. So I'm not substituting data, but you can solve such questions. So that is how you can analyze such problems. Okay, more such problems were given, but let me go to another concept. Let me take up a problem where this is very differently placed, and there is another problem which I will extend to this. Let's understand what is the problem. Refractive index of atmosphere around a planet varies with altitude h. According to the equation, mu is equal to mu naught minus kh, right? Mu naught and k are positive constants denoting the radius. So what he is trying to say is, let's say this is the planet. The diameter of the planet is 2r. At any position, we are above, like if I draw like maybe at any location. So you are here, let's say you're sitting here. The distance is h above the surface. So you know the refractive index which is present here. So indirectly, it seems that if I draw a spherical shell, refractive index throughout is same. That seems. Now, layer by layer, refractive index is changing. So question was, what should be the altitude? What should be the value of h for a point such that a flash of light spreads around the planet in a spherical layer concentric with the planet in addition to the other directions? So basically, he's saying that if you take a torch light and you just spread it at this point, you focus it at this point, this ray, this wavefront starts circulating around our planet. That is what he is trying to tell me. Now, how do I observe this question? To begin with, I think that if I'm sitting at H and I move a differential distance dh outwards, so I reach this point. So this distance is H, this is dh. I know that refractive index here and here is not the same. And I want my beam to move in a circular path. So what I'm trying, take a differential segment, take a differential movement of this wavefront and the differential movement of this wavefront. Understand one thing, as you are moving outwards, mu, as h is increasing, mu is decreasing. So speed is increasing. So in a given dt time, these wavefronts will move higher distance and they will move lesser distance. And if they move appropriate distance such that if I join this line, it subtend angle d theta, my purpose is solved. Then it will keep on rotating. Keep on rotating. If this is satisfied, obviously it will rotate. So I'll give some dt time. And for the dt, I will try. So how will I think? So if I say that my front guy at h travels, so use angle is equal to arc upon radius. So he travels h d theta. My other guy, I mean, I've drawn a line, but it's a small arc. It travels h plus dh into d theta. Practically, how much it travels in. So you understand that there is a relation between these two movements. And if I write them as dl1, dl2, I also know that for a dt time, the distance that they will travel will depend upon the velocity. So give them equal dt time. Dt time is basically some differential phase that I am providing the two wavefronts. That will vary linearly with respect to time. So I'm saying if the velocities here were v1 and the velocities here were v2, their travel distance will be v1 dt and v2 dt respectively. And what are these distances that you can write? v1 dt, v2 dt. So keep dt as such. Write v1, that is c by mu, and that is whatever is mu here. And this will be dt into c upon whatever is mu there, which is mu plus d mu, or you can say mu naught. What is that? This is mu naught minus kh. That is the value of mu here. And technically, I should say mu here. I'll write it actually. It is d mu for me is minus k dh. That is coming out as d mu. So what is mu for this layer? Here it is mu naught minus kh, and here it is mu naught minus kh minus kdh. So just you can write mu naught minus k into h plus dh. I mean, that's what we can do. So now everything is very well defined. Take ratios and try to solve for h. So what should I do now? Take the ratio of these terms. So h plus dh into d theta upon h d theta is basically equal to this distance v2 dt. So dt into c upon mu naught minus, all will cancel, h plus dh upon dt into c upon mu naught minus kh. I could have directly equated with the optical path length. The only thing why I'm writing this is just to explain a bit more. Or objective question, I can directly like c dt c d theta d theta. I could have directly gone with this because this gives me mu naught minus kh upon mu naught minus kh minus kdh. That comes out as h plus dh. So what we are getting upon h. Now just take binomial approximation and write the answer. Give me a value of h for which it is satisfied. So I think it will be much more simpler if I write it as 1 minus kdh upon mu naught minus kh. and write it as 1 plus dH upon H. Just observe. So this term will cancel out, and dH will also cancel out. So minus KH is coming out as mu naught term minus KH. Just check this term carefully. Have I missed a negative term somewhere?
It is plus KH.
Where?
Left hand.
This is mu naught plus KH?
Yes, left, sir. We did 1 minus KDH. That is 1 plus KDH.
Acha, acha. I have written 1 my. Okay. Oh, yes. Here it was plus. No? Now, how it is plus? Mu naught minus KH minus KDH. So it should be, I have divided by mu naught minus KH. So I'll have 1 minus KDH. Just check.
We're bringing it to numerator, so we'll get another minus sign. We have 1 by 1 minus KDH by mu naught minus K.
Okay. I have taken a binomial approximation and should have taken in a more appropriate way. Okay. So I could have directly written here. I mean, it was not required. So I should have done it here itself. I would have got 1 minus, then I could have brought it in the numerator after the binomial approximation. I should have written K dH upon mu naught minus KH. Yeah, now it is fine.
Yes, sir.
LHS. And that is again 1 plus, and this is 1 plus dH upon H, and HH cancel, DH cancels, and solve for the result. DH cancels, and you'll get your answer. Just took the binomial approximation properly. So you have divided by mu naught minus KH, and then the power will come into numerator, and 1 plus NX I have written. So you'll get my answer. So you'll get the value of H. What I'm trying to explain in this problem is that in such problems, it was very interestingly put up. I mean, we are at a distance of H from the surface. So this distance was known to me R. I was at a distance of H from the surface. I have thrown a laser beam in such a way that I want that beam to encircle it. And obviously, for a unique height where that beam has been thrown, it will definitely encircle. So it is only about throwing it at a unique height so that in equal time intervals, whatever is the movement of the wavefront, if I draw a new, so like physically the concept is of wave optics, that if this was my wavefront to begin with, my wavefront will have a changed shape, but that should, if that hits, like the line of action hits the center, the circle is dead sure, for sure, and you will get your answer. So from here, you can find out the value of H, you cancel it, and you will get 2kH, and that comes out as mu naught. So H comes out as mu naught by 2k. So that will be your answer to the question. All right, so let me take up another different problem. Just look into this question. Very often, you will see an insect dragging an object much larger and heavier than it. Now, it is based on rotational mechanics. What is happening here? The figure is a top view of an ant dragging a straw that is much larger and heavier than the ant. This is a straw, this is a top view, so gravity here is in the cross direction. The ant pulls the straw at one end, rotating it slightly. Just give me a moment. You read the question, I'll just. The ant pulls the straw at one end, rotating it slightly, and then it does the same action at the other end, and so on. How does this technique work, right? And basically the question is, if the ant is dragging a straw of mass small m on a horizontal floor by this technique, coefficient of friction between the straw and the floor is mu, then you have to find out the force that he has to apply. We need to calculate the value of force that he has to apply here. Now see, in the last class also I've given you one question which was based on a similar concept. Let's see how you solve this question. Think about it. Because while you analyze this body, the guy who is applying the force wants to make sure, I mean, pull, push, whatever it is, that this rod starts moving. So if I just look into the forces which are acting on the body, what are the forces? I'm not interested in weight normal reaction as such. Basically, my interest is the pulling force which he is applying, the ant is applying here. Let's say that force is F at the corner, the pull that has been applied. And that should be sufficient to overcome the limiting friction. Now the problem is, if the ant was applying the force from the center, right? All these differential limiting frictions will act in the opposite direction, like this. And then because they are of symmetric distribution, the torque because of these frictional forces about the center is 0. I could have applied the net friction at the center, which I can't do here because he's applying the force from the corner. So I need to look into the spectrum of the question. It seems when you try to pull, these guys go here, those guys come down. So because they're going like up, I need to apply some forces down here. Some forces down here. I don't know the location. And they are going down. So I need to apply some forces here. Don't go into the length of these vectors. I'm basically trying to analyze the pattern of this problem. So what I'm trying to say, the concept behind the problem is, that now these vectors can be consolidated at their midpoint by one force, because like point of action of force is a point about which the torque of the differential force is 0. So whatever is this length, you can consolidate one force at its center, and whatever is this length, you can consolidate one guy here. I'll come to that point. But basically in this problem now I have three distinct guys, F1, F2 and F, and this is my free body. So first equation that I can write by balancing is F plus F2. To just move it should be F1 first, and secondly, the total force of friction F1 plus F2 should be equal to mu mg. Remember, even if I take differential segments which are about to move, on every differential segment, mu dmg, I don't know the length of this part. So I don't know how much is acting here, how much is acting here. But the sum of magnitude of these forces will be the total friction. Very interesting point I'm making here. Observe carefully. Every differential segment, mu dmg. So all mu dmg's there. So the sum of their magnitudes is the net magnitude, which is mu mg. That is my second equation. Thirdly, as I don't know the length, but I know the point of action. So I'll assume this distance to be some x. This distance is again L minus x. So my distribution is like x by 2. This is midpoint. Now this distance is L minus x by 2. And this is L minus x by 2. So you know all the distances as such now. So let me make a statement that the force F1 and F2 will be dependent on the mass, and mass will be dependent upon length. So basically it is x upon L minus x. Now I have made few statements properly. Also, so this is only force balance and distribution pattern balance. And fourth, I can do the torque balance. It is just about to move. So let me simply balance it about any point. I'll try to balance it here. So F1 into x by 2, the torque about the corner clock. I'm just writing the magnitude is balanced by F2 into x plus L minus x by 2. So L plus x by 2. Just check that I've written x plus L minus x by 2. So 2x plus L minus x, L plus x by 2. Perfect. So this 2 will cancel out. Now I have all the equations to be solved. Let us try to find out what force he has to apply. So now all of you just go through these equations as fast as possible and try to yield the value of F. Let me check what are we getting, because f1 upon f2. So first of all, we'll get the value of x from here, right? And this was f1, remember, f1 into x bar. So by third and fourth, directly if I solve, I'm getting x upon L minus x is L plus x upon x. So basically 2x square is L square. So x is equal to L by root 2. Negative root does not have any significance. I'll take the positive here. So now, at least, now this can be a perfect objective question for IIT. You can a multi-correct, he can always ask that if the ant is trying to pull, but maybe he won't give you that hint also, because if he asks, the hint will come to the student that what is the point from where the direction of frictional force is reverse. And that point is at a distance of L by root 2 from this corner. X is L by root 2. Depending upon the value of x now, f1, f2 is what we are looking into. So we should get our answers. Check what is that we are getting. Because f1 plus f2 is mu mg now, and f1 upon f2. So directly by second, which is sum of these two, I'll use ratio and proportion directly, mu mg. And the ratio, third, f1 upon f2 is x upon L minus x. So it is L upon root 2 upon L minus L upon root 2 is basically 1 upon root 2 minus 1. So my answer is f1 should be 1 upon root 2 times mu mg. And f2 should be root 2 minus 1 upon root 2 times mu mg. You understand what I have? So just taken the ratio here. 1 is to root 2 minus 1 plus 1 root 2. And there's a root 2 minus 1. So simply I've solved the equations. I got f1, f2. I got f1, f2. So my answer to the question is f, which is f1 minus f. And what is that? Just get the value. So it is like mu mg upon root 2. And it is 1 minus root 2 plus 1. f1 minus f2. 1 minus root 2 plus 1. So 2 minus root 2. So mu mg into root 2 minus 1. That should be the answer. And remember, this factor root 2 minus 1 is less than 1. So indirectly, you understand why this question was being framed this way. The question is, if the ant started to pull or push from the center, the amount of force that was required was mu mg. But by a bit of planning, the amount of force which has been required now is mu mg into root 2 minus 1. So that is now less than mu mg. So whenever he'll try to pull from the corner, he will have to put less effort. So that is what you have to explain in this subjective problem. How does the technique work? But value is straightforward. So you will get your answer. How much force has to be applied? Okay. Let me take once. Avinash, yes. What is the point? Yeah.
Normal force pattern, how does it look in these figures?
Didn't get you. Can you come again and be clear?
How is the normal force looking in this diagram on the rods from the ground?
How will the normal force from the ground? That will be uniformly spread.
Friction is nothing but mu into n, right, sir? If mu into n is same, if n is same, mu n should be same. So why is there a change?
No. Mu n is same. The distribution of direction is different. Mu n in magnitude, because if you look into any differential element, the dm mass of the element is same. So as far as the vertical free body is concerned into the plane, every dmg downward and dn upward is symmetric. The problem is static friction magnitude is no issue. It is mu dn. So that's why I've drawn forces of equal magnitude. The problem is with the direction, because when you start to pull it from this side, every point on the rod will not have the same tendency. The direction in which the rod elements will have a tendency to move, those directions are anti. So I just said in the beginning that if you will pull from the center, all the points on the rod will have a same tendency to move, a same direction in which it will have a tendency to move. But if you try to pull it from corner, the tendencies are different. You understand that if you take a frictionless rod and you rotate, try to pull it from this side. Whenever you have to understand the effect of friction, remove friction and think. We understand that these points will have one directional tendency. Immediately after applying the force, another guys here will have this tendency. I don't know about which point what is happening. So I just presumed it, because this problem cannot be equated exactly with a smooth surface. So I cannot directly come to the center of mass. So I knew this thing, that because of the balances, I need to balance the force on the torque, because we are in a situation where we are just about to move. So I said that I know the tendencies are going to be different. I will assume some point. Once I assume the point of action, my results were very evident. So this X definitely depends upon the magnitude of friction and the end where the ant is applying the force also. Because you understand the calculation of X depends upon the torque balance about this point or any other point. Because I'm just balancing the system. Right. Let me just share one concept with you. I just wanted to share. While the vector methods are very useful in solving a lot of problems in kinematics, I'll just take a small example. Anything like I've seen students solving problems where they say that maximize the range, then generally people write equations of X and Y, then they start writing quadratic equations, and then they take discriminant, maximum, minimum, and whatnot. Remember one thing, any problem which is based on vector methods are very strong geometrical methods. Just this point came through the problem. Geometry can be very strongly used in any problem which is based on 2D or 3D. Small things I will explain to you, and if I have sufficient time here. Like, I don't know if you remember this problem or not, very standard problem, that if there is a river which is going as such, and there is a guy who wants to cross the river. There are two situations in which he crosses the river and reaches the same point. Listen to the data carefully. I have not got that question, so I'll read that data for you. So he starts from this point, and in both the cases, he reaches here. And the point where he reaches is 30° downstream with respect to the downstream direction. This is the downstream direction. The question is, he reaches here twice. And in first go, he reaches here in 2 minutes. In second go, he reaches here in 4 minutes. And in both the cases, he reaches a point which is 30° downstream. And river velocity VW is not given to you. You need to find out the river velocity. So what is given to you? This 30 is given. In both the situations with respect to Earth, a student is reaching here T1 in maybe 2 minutes, and T2 is taking 4 minutes, given to you, right? This is given to you. And velocity of that guy, that boy, with respect to river or water, whatever you say, water, in both these situations has got the same fixed magnitude. That has some value. Maybe in this problem, I will share that value with you. I don't remember what value they have given. So that value is √3 meter per second. Can you solve this in one line? Like least calculation, and can you give me this time? This velocity. Think. Two minutes, 4 minutes, nothing is given, no width given, 30° given, 2 minute, 4 minute given, velocity of boy with respect to water given, but velocity of water with respect to Earth not given. This is what is required. Why I took this problem is, the previous problem was exhibiting some geometry. Beautiful geometry can be used to solve this problem in like 1-2 line. Now, whenever such questions come, or any question on projectile, any kinematical question comes in multi-dimension, please don't use I, J, K and all these things. It will take a lot of time. If you use vector concepts, your problems will be very simple. So when I see this problem, how I observe it is, now I will draw something and you interpret what I'm doing. First of all, I'll draw a vector. It will have, just focus on this. It will have some value VW. Then at the tip of this vector, I will draw a circle. I'll draw a circle whose magnitude is √3. So I'll draw a circle of magnitude √3. And then from the tail, I'll draw a line which is at 30 degrees. And this will cut the circle at 2 points. One point is here. This value is √3. One point is here. This value is also √3. Now, if I just solve the geometry of this triangle, I'm done with the question. I've used triangle law of vector addition. Basically, what I'm saying is, if this is the velocity of river and this is the vector √3, like this, the resultant becomes this. And along this resultant, this guy travels. He may take 2 minutes, 4 minutes, whatever it is. And secondly, again, the river is the same. Now he jumps like in this direction. And the resultant is this. Not only this, that I know this, I also know one more thing, that the second time he took, if he is taking less time, I mean half time, that means the velocity is twice. So basically, if this side is V in length, then the long guy is of length 2V. So basically now it's a simple geometry problem. This edge is V, this is 2V. So this edge is also V. Forget vectors now. This line √3, this line √3, this line VW. VW needs to be calculated. So what I will do now, I'll drop a perpendicular from this side on this chord. Now remember, if this is V, this is V by 2, this is also V by 2. Just use Pythagoras theorem. The square of this side will be VW square minus V plus V by 2 is 3V by 2 square. And that will be equal to, if I look into the square of this side from this right angle triangle, it is √3 square minus this square. So √3 square minus V by 2 the square. So I got one equation between V and VW. What is this V? This V is the net speed of the boy with respect to Earth in one case and 2V in the other case. 2V when he will take less time, which is half, and V in this case when he will take more time. So the factor of time is the factor of velocity. So I directly took that factor 2. Observe it carefully. So I got V plus V by 2, 3V by 2 square, and this is VW square. And then in that triangle I worked out, this was 90. And one equation I will use by cosine rule, simply cos 30, I'll write √3 by 2 is this square plus this square. So VW square plus 2V square minus 2 VW into 2V, VW into 2V upon. So this square plus this square minus this upon twice of the product of those two sides. So it is VW into V. If you just look into these equations carefully, I think V and VW both will be solved. Matlab, you do anything you wish. I was not interested in this calculation. I know you people can solve it far more easily. But if this triangle is known to you, this √3 is known, 30 is known, the two unknowns V and VW, which are side lengths appropriately, can be solved. I just wrote something. I applied Pythagoras. And I don't want you to use more angles, or I can use the property of isosceles triangle. I can take theta, exterior, interior, everything we can do, sine rule, cosine rule. Whatever works for you, go with that. But idea is you'll get your answer by this. So that's what I wanted to tell. One more thing. Let's say somebody says, and just look into the result that I'm deriving. Just try to understand the philosophy. I mean, that result may be something which is known to you, but I wanted to give you the thought process. The thing is, let's say when we solve a object being thrown from the surface on an incline. Why? Because I've seen n number of things that a student do. This is the angle of incline, let's say theta. You throw a ball from here. Ball lands at some position. So by vector approach, I will only draw two lines. I will say this is my ut, this is my half gt square. I'm done with my problem. Why should I analyze a parabola? I should never analyze a parabola. It is never required. If you throw a particle from here, this is, let's say, your u, and you throw a particle at an angle of alpha, and your incline is at an angle of theta. You want me to solve time of flight, range, whatever is required. I will say, basically in 2D, my equation is ut plus half at square. So I said a vector is g vector downwards. So this guy is half gt square, vertically downwards. And this guy is my ut. So now in this triangle, I have this angle, which is alpha minus theta. Fine. So if you want me to find out any other parameter like time, I may use sine rule, cosine rule in this triangle. I'll know this is my range, R. Now, why I was using this? If I ask someone to derive a condition when the range is maximum, now intelligently, if I use, I can diminish the sides of these three, the sides of this triangle by a factor of t. I will form a new velocity triangle. If I can explain that to you, I'll form a vector whose value is u. I've divided this by t. I'll divide this by t again. I divide this by t again. So I'll form a similar triangle. I'll form a similar triangle here. This is u. This is gt by 2. And this side now is r by t. R by t. Remember, this angle is theta, the angle of incline. And this is alpha minus theta. Now, he can say, find out a condition when range is maximum. Now, you can understand that range is basically the product. Range is something which is proportional to the product of this vector and this vector. But the product of these two sides is something which is proportional to the area of this triangle. Area of this triangle. Mark my words. I have a triangle now. U is a known constant. G by 2 constant. T is a variable. R is a variable. So these vectors may have different size, but their directions are fixed. Theta is fixed. So this vector has a fixed direction. GT by 2, this is actually downward. Like I've just drawn it. This vector is downward. Its size is GT by 2. And this is a vector whose direction can change, but whose magnitude is fixed. U. It can move anywhere in this domain. From theta to 90, he can go so that the particle lands here. He can go anywhere up to this domain so that the particle lands here. So my question that comes to my mind is, I have a rod whose size is u. I can rotate it from theta to 90. As I rotate this rod, the landing angle is fixed. So obviously this length and this length and this length changes, but their direction is fixed. So I'll search for that orientation of this rod so that the area enclosed by the triangle becomes maximum. And you know a fundamental geometry that is possible if this side is along the bisector of all the possible positions. So what I'm saying is, if one side of triangle is fixed inside, right, on the basis of his orientation, it can move in a circle. I mean, whichever way you want to think, it can move in a circle between this point and this point. So out of all the possible positions that I can have for this guy, this vector u, forget about this vertical, horizontal, they will manage on their own. So you basically move your u from theta 90 to theta, move this u here, all the positions. You can understand as you are moving here, just to give you a glimpse, the area enclosed increases, and after the bisecting point, it decreases to 0. So directly I will say that when it is along the bisector, so when alpha is equal to theta plus pi by 2 upon 2, this will be the time instance when it is along the bisector of these two, theta and 90 ke bilkul center mein aayega, then it will be maximum. So R is max if alpha is this. This I can say because I know the property of triangle. Even when you derive that result, if you just rotate this diagram, all the projectiles that you study on a table, like fundamental. The only thing is theta is 0. So your triangle, instead of a tilted triangle, your triangle becomes this. So there what you do is you take your ut like this and you take your half gt square like this, and this is your range. And then you diminish it by t. So this becomes u, and this becomes gt by 2. This becomes r by t. And the area of this right angle triangle is something which is proportional to the range. So there again, what happens is, out of all the possible positions, I search for, so now this becomes a question of a rod. If you give me a rod of length u, and the rod is slipping with respect to the vertical till the horizontal, what is the position of the rod where the angle enclosed by this triangle is maximum? And out of all the position, that position is at 45 degree. That's why we say that at 45 the range is maximum, not by writing the projectile equation sine 2 theta is equal to 1. That is not a thoughtful way of solving physics. Should be done by geometry, because we have very little time to engage you. But the complete kinematics don't require calculus. If you start thinking in terms of geometry, there are beautiful patterns. These patterns need to be observed. Once you get the idea, just think it like this. Any river, boat, whatever you do, one method you always obviously know, I cap, J cap. So do whatever you want. But please think in terms of vectors and geometry. Your problem will become very simple. So just think about what I have said here, why 45, and I've extended this idea to an incline. Now you understand I can make n number of problems. I can go to a building, I can throw a projectile motion, it lands somewhere, find range, find time, angle for which the range is maximum, anything. So I won't write those I cap, J cap, XY quadratic equations. I will draw a vector diagram. I will make a triangle for displacements. I will diminish that triangle to a similar triangle by a factor of t, so that I start working in terms of velocity. Remember, one triangle is working for displacements. And when you divide it by t, your vectors are talking about velocities. So my velocities, my displacements, my angles of velocities, everything lies within the triangle. I will just form triangle. I'll solve its area. I'll get my answers. Bye-bye and take care.